wanted to show you that I posted the exam key in Blackboard for exam 1. So I know it's been over a week, and my goal is to do this sooner next time because I like to give you better feedback quicker, but you know, better late than never. And so if you're on Blackboard like this, then you should go to Online Classroom. And when you do that, you scroll down, now you see there's a new folder down here. It says Exam Keys. So if you click on Keys, there's the exam 1 key, and you click on that, and here's what it looks like. I've essentially, if we would have had exam in paper form, it would have looked more like this. And I've just gone through and answered everything. Now I know you've had the multiple choice answers for a while already, but I went in and added some comments on certain ones. I just noticed there were a few questions that like people tend to miss more than others. And if that was the case, if I felt like it was a multiple choice question that a lot of people missed, I put some explanations in. The one about the octet rule and why the correct answer there was not all of the above, which, by the way, there's a typo down here. This should not say none of the above. It should say all of the above. Sorry about that. But anyways, a lot of people picked all of the above on this particular multiple choice question, if you remember the one about the octet rule. So I put some explanations in there as far as why certain ones were false and why only B was the correct answer. Scroll on down, you can see I worked out the specific heat problem. And I think I also worked out the temperature conversion problem down here about the one with the blood and the cooler. Okay, it's not scrolling up for me. There it goes. Sorry. I kept trying, my screen like froze a little bit. I need to go back. Okay, there's the temperature conversion problem. So work that one out. Anyways, I just put some added comments. So if you have any questions about any of those multiple choice and why you missed what you missed, or why, the right answer was the right answer, then please email me.
I was just
Oh, go ahead. Somebody was saying something.
no, you're good. That was me. I'm sorry.
Okay. All right, right here, I wanted to say too, this blood serum question. I put a note here. I said these problems were pulled from the homework, chapter 3, Mastering Chemistry homework problems. So sometimes I do that. Sometimes I'll pull a homework question directly from your Mastering Chemistry. Now I change up the numbers a little bit, and I had you solve for grams instead of like liters or milliliters, but it's the same exact concept. Also, sometimes I'll pull a question from the back of the chapter. You know how I give those lists? Here's the problems I recommend you work from the back of each chapter. Sometimes I'll pull a problem that you maybe didn't work or wasn't on that list, but it's still right there in the back of the chapter, or one from that list. So if there's any incentive for you to take your homeworks very seriously and do well on them and get your questions answered, or if there's any incentive to do those textbook problems, you may find those problems again on the exam. Let me see if it'll let me scroll up. Okay, maybe. God, my computer is being slow right now. Okay. Another thing I wanted to point out is, let me zoom in. A lot of people, sorry guys, I'm having some, it's not letting me do much. Okay, this neutrons thing right here. Oh my gosh. Sorry, hold on. Okay, I have no idea where we are now. This is the last problem, the word problem. That's not what I wanted to look at right now. I just need to be more patient. Okay, let me scroll back up. I wanted to go to that table where we filled in all the info on the atoms, the number of protons, neutrons, electrons. A lot of people, when you were telling me how many neutrons are in an atom, they put decimals on that number. And, okay, right there. Don't move, computer. Okay, they put decimals on these numbers. And it was important that those were not decimals. You can't have half a neutron or a third of a neutron. So that was important that that was a whole number. And then a lot of people told me vanadium had 5 valence electrons. And remember, we talked about how transition metals, all transition metals have 2 valence. Now, yes, vanadium forms a metal with a +5 charge. But that's because after they lose their valence electrons, those 2, they sometimes, transition metals, lose additional electrons. And we talked about that in lecture. So anyways, that was some common errors on this table. The rest of this about the physical chemical changes, this was pretty solid. Most people did pretty well on it. And then I wanted to show you this last problem. If you have a question about how to work out the word problem, I worked that out down here. The issue with this, some people got the answer 50.9 days, but then you rounded to 60 because in your head, maybe you thought 59 instead of 50.9. And I didn't take a lot of points off, if any, for that minor error, okay? Because you worked the problem entirely right, okay? Also, if you got bonus questions, or sorry, if you got bonus points from the discussion board stuff, I put those bonus points, I added it to the score for your last question here. So this last question was out of 10 points. And if you got all of this correct and you got all 5 bonus points, you should see a 15 out of 10 on that particular problem, okay? But I did, if you got bonus points, I made a comment in the, you should, can you guys see my comments on the exam? Like where if I type something like great job, or this is what you did wrong, or you rounded wrong. Okay, good. So I typed there, hey, I gave you 3 bonus points or 5 bonus points or 2 bonus or whatever. So if you're having a question about that, that should be available to you. But go through and look at that as you want to, because that is now available. And I would love to hear from you guys too. No, I don't want to share anymore. How did the exam go overall? Any feedback from you guys on the exam? Was taking the picture and uploading it as a PDF okay? Did y'all figure that out okay? Was it a headache for anybody? Okay, got that done pretty good. Okay, good. Any other questions, please, if you can? I know some of you've already emailed me, but if you can, please have your video on. If you've already emailed me about it, that's okay.
A question.
Yes, Emmy.
Okay, so whenever I went to take pictures of my work with the Scannable app or whatever,
Yeah.
it didn't work. And so I just had to turn it in without that. And I was already rushed for time, so I was freaking out. But is that okay if I'm not using Scannable?
Oh yeah, you don't have to use Scannable. That was just an app
Oh.
that I said a lot of students did find helpful. If you
Okay.
can get it to work in future, great. But if you just need to email them to me, that's fine. If you ever have, and a lot of people did email me their stuff. And if I didn't respond to you, I'm sorry. Normally I try to say, got it, thanks. But I usually get busy grading and I forget to respond to everybody's emails if you emailed me pictures of your work. Question in the chat, how do you see your comments on our exam? Madison, if you did pretty good on the exam, and you didn't miss a lot, you may not have any comments. If you notice, like on really the only one I probably made comments on was that last file response question. So if you don't see any comments on that, it may be for 2 reasons. Maybe you got all your points on that, or I only typed how many bonus points I added, but that should probably be the only one I put comments on. In future, if I have a file response question, that's usually the one I provide comments on. Does that help answer your question, Madison? Okay. All right, well, I really do just want to check in every once in a while and make sure you guys feel like you're swimming at least and not sinking in this course. I know we have a lot going on this week. You had the Lewis structure dry lab due last night. If you have questions on Lewis structure, I'll take the time to say, do not just tuck those questions away. Lewis structures are a big part of exam 2 and condensed structures and all that. And what we're doing today builds off of that. So please make sure you reach out to me or set up a Zoom with me or drop in on my office hours if you have questions on those, because we're going to build on that today. We're going to do molecular geometry. We're going to finish chapter 4, and then Friday we're going right into chapter 5. Likely from this morning's lecture, gauging on time, I'm going to have to upload maybe a 10 to 12 minute video to cover the last topic in chapter 4, which is going to be how to name binary covalent compounds. And I'm sorry for that. I hate it when I have to do that. But it's not going to be a half-hour long video. It's just going to be a quick, 10-minute video or so. But I will give you more info about that depending on where we land with the material today. So you should have chapter 4 stuff. Don't forget as well, other things this week, your quiz number 4, if you haven't already taken it, is available now, and that's due by the end of the day. And then your chapter 4 homework is due Friday at midnight, okay, on mastering chemistry. And I think that's it. Okay, let's get into lecture material. So we're going to pick up where the video left off from last week. Molecular geometry. So it looks like this. And as a reminder, we are now talking about covalent bonds, not ionic bonds. Can somebody help remind me or the class, how is a covalent bond different from an ionic bond?
Covalent bonds share electrons instead
Keegan,
of gain or losing.
that's perfect. Covalent bonds share electrons. So remember that today. We're not dealing with ions, we're sharing electrons. And remember, we're still abiding by the octet rule. So every time you share, you still want to achieve 8 electrons. And I walked through from that video lecture last week how every atom abides by the octet rule, okay? And questions to ask yourself. How do you know how many bonds a particular atom like carbon or nitrogen or fluorine are going to form in a covalently bonded molecule, okay? We had that motto, every time an atom shares an electron, you quote, gain an electron by sharing. So remember those things. And if you have questions, please reach out. But now we're going to talk today about molecular geometry. Okay. We introduced Lewis structures and condensed structures, and we've spent a lot of time working on that from the lab. And those are helpful. Why did we say they're helpful? They're helpful because they help us see how atoms are connected. How they're arranged, okay? But we have to take it one step further. A Lewis structure is a 2-dimensional representation of a molecule, okay? But we are not 2-dimensional beings. We're 3-dimensional. We live in a 3-dimensional world. So geometry is going to help us imagine these molecules and how they interact in 3 dimensions, okay? Things take up space. And this becomes more and more important the higher you climb in different health sciences, especially towards fields like nursing. Maybe you communication majors, not so much, but it is helpful to know these things. So Lewis structures help us keep track of valence electrons and the geometry. And remember, geometry is just a fancy word for the shape of molecules, okay? And electrons, their location in an atom or in the molecule determines the geometry. So as you see, with everything in chemistry, electrons are the foundational thing here. They're the reason why. So here's some examples, some different pictures of molecules with different geometry. These models with the different color spheres, we call them stick and ball models or space filling. No, these are space filling models. These are just more ball and stick sphere type models. But what you see here, there's things you see and there's things you don't see. What is visible in each of these? The different colors, the black, for example, with CH4, the black and the white, you've got the atoms, okay, this would be the carbon, and then the hydrogens are the white spheres. You can see the atoms, okay? So the visible part, one part that's visible are all the atoms in the molecule. The other part that's visible are the dashes or the lines or the sticks connecting the spheres. And these are the bonds. These represent the bonds. So we can see the atoms and the bonds, but what can we not see? Something else that's really important that we just said is the electrons. We cannot see lone pairs. Okay, and if you take some time and look through these closely from what we talked about last week in the video lecture, nitrogen, okay, we got NH3 right here. Remember that nitrogen has to have how many bonds and how many lone pairs in a molecule? Anybody remember?
Isn't it 3 bonds and then 1 lone pair?
Thank you, Kendall. Yes, 3 bonds and a lone pair. So if we drew it in, we don't see that lone pair, but it's there. We could draw a lone pair in on that nitrogen. And sometimes you'll see people draw like a lobe around it like this, okay? So we don't visualize the actual lone pairs when we draw the geometries, but they are there and they do help us determine geometry, okay? All right, now everything that geometry is built on, there's a model and it's called the VSEPR model. This is kind of just the concept behind how we derive and how we determine the geometry of a molecule. What does it stand for? It stands for valence, shell, electron, I'm just going to abbreviate, electron pair, repulsion. Valence shell electron pair repulsion. That's what the VSEPR model stands for. And again, here we're talking about how electrons, they repulse one another, okay? Because they're negatively charged. We know opposites attract, like charges repel. So when electron lone pairs or electrons kind of get close to each other, they push away, they push other atoms away because atoms have electrons too. And that's what forces the geometry, okay? And that's kind of what I have stated down here. Electrons in the bonds, remember bonds have how many electrons in them? Any dash or any line represents how many electrons? Yes, 2. Okay, so bonds have electrons and lone pairs, and they all repel one another, and they get as far apart as possible, and this is what forces the shape or the geometry. Okay. All right, so let's look at kind of the way we walked through with Lewis structures. We said there were 5 rules, and then we walked through step by step what are those 5 rules for how to draw a Lewis structure. We're going to do the same thing here, but this time with geometry. So how do we name the geometry of an atom or a molecule? There's 3 rules that are going to set us up to get this right. So rule number 1 is that you're always going to start by drawing the Lewis structure. And then you're going to identify what atom am I trying to name the geometry for. Okay, so this points out an important thing, that you're not naming the geometry of every single atom in a molecule. You are only going to name the geometry. Usually it's the central atoms, okay? You're not going to name the geometry for every atom in a molecule. You will name the geometry for central atoms. How do I know if an atom is central or not? Can anybody help me answer that question? How do we know if an atom is central or cannot be a central atom? We talked about this with Lewis structures.
It can form more than one bond.
Yep, thank you, Keegan. Do you guys remember? I'm going to scroll up for just a second. Do you guys remember the slide up here? And I wrote, when I walked through it in the lecture, I said, this is a key. I want you to think of this as a key, and I want you to use this slide. And we drew out all different kinds of pictures. We said carbon can look this way, carbon can look 2 double, and I did this whole slide. And then I drew a big fat line right here. And I said anything to the left of this line can be central atoms. Okay, anything to the right, like hydrogen, halogens, they cannot be central atoms. So anything in main groups 4, 5, or 6, carbon, nitrogen, oxygen are just examples of elements in main groups 4, 5, and 6. These can all be central atoms, okay? We can name the geometry for those atoms. We're never going to name the geometry for halogens or hydrogens, okay? So just a little review there. Let's go back down. Okay, okay, then step number 2 is you're going to find the number of charge clouds. What is a charge cloud? This is a new phrase. Okay, it's kind of like a new vocabulary term here. A charge cloud is either a bond or a lone pair. Okay, so bonds, including double and triple bonds, they count as one charge cloud. Okay, and then lone pairs each count as one charge cloud. Now, you're going to see me adjust the phrasing a little bit as we go on. Sometimes instead of counting bonds, it's much easier, I should say, if you count the number of atoms that are bonded to your central atom, okay? I'm going to say that again. Sometimes it's easier to count. I use the phrase bonded atoms instead of just counting bonds, because people are going to be tempted to do this. They're going to be tempted to say, okay, atom X is bonded with a triple bond to atom Y, and they're going to count 3 bonds. And you're not wrong. That is 3 bonds. But remember, we count double and triple bonds as one charge cloud. Okay. That's why for me, I like to look at this and say, okay, if atom X is my central atom, how many different atoms is it bonded to? How many bonded atoms do I have here? Well, I know that it's bonded to atom Z. There's 1 bonded atom, and atom Y, there's 2 bonded atoms, okay? And you count it so on and so forth like that, instead of just counting bonds, so that you don't get it wrong. We'll do more examples of this in the future, okay? But anyways, the goal is you find the number of charge clouds, okay? By counting bonded atoms or bonds, and by counting lone pairs. And you're gonna add that up and get the total number between the bonds and the lone pairs. Then you're gonna look at this table down below, I'm gonna show you, and this will help you predict the shape. Okay, because again, things move as far away from each other as possible, and that forces a certain geometry. Okay, here's this table. Again, this is kind of another key of sorts. I would have that page, that slide that I just scrolled up to earlier, and I would have this table ready, printed out, available for you to use on exam day. This is gonna be so handy, okay? Don't waste all this time memorizing this. Now, if you were doing my class face-to-face, my exams are not open note, open book, and you would have to memorize this stuff. but consider yourself fortunate that you can have this ready and available. This table is very, very handy. One adjustment I'm going to make on this table really quick though, instead of number of bonds, I'm going to say number of bonded atoms. Okay, I know I just said that earlier, but I'm making this a really big deal because as you count number of bonds, people would be tempted. I'm going to show you a really good example. We're trying to name the geometry in a molecule of carbon dioxide. You're going to look here and say, oh, carbon's got 4 bonds. And yes, carbon should always have 4 bonds, but that's going to mislead you to the geometry. Okay, that's not going to be correct here. You remember we count double bonds and triple bonds as one charge cloud. Okay, we're trying to count charge clouds here. So instead of counting bonds, just count the number, how many different atoms are bonded to carbon. We've got 1 oxygen here. And I shouldn't say different atoms. How many atoms are bonded to carbon? We've got 2 oxygen atoms bonded to carbon. Okay, so I've got 2. All right, that would be an example. Counting the number of bonded atoms instead of bonds. How many lone pairs are on carbon? 0. And remember, I do know that oxygen technically does have 2 lone pairs, each of those oxygens, but we are not trying to name the geometry of exterior or perimeter atoms. We're trying to name the geometry of our central atom. And carbon is the central atom in this case, and carbon has no lone pairs. Carbon should never have lone pairs, right? So if we're counting the number of bonded atoms, we get 2. If we're counting the number of lone pairs on the central atom, we get 0. So that means total charge clouds is a total of 2 when you add these columns up, and that's what you're going to do. All these first 2 columns add up to give us the third column. Okay, and then once we know we have 2 charge clouds, we just look straight over to the next column, and the name for that, any molecule that adds up to 2 charge clouds is a linear molecule. The only way those exterior atoms can be oriented far apart as possible is 180 degrees. All right, so again, the example it shows you here is carbon dioxide. Okay, that's just what we walk through. We are going to spend the next several slides walking through this entire table step by step. So I'm not going to spend a lot of time on the whole table right now, but that's how you use the table. You add up the number of bonded atoms, the number of lone pairs, and you see the total number of charge clouds, and then you look over and you name the geometry. Okay, the geometries are right here. A lot of people, by the way, have questions on how to say this one. How do you guys think we're going to say this one? Which honestly, you're never going to have to say it to me because we're not face to face, but when you're writing it or when you're saying it to each other, this is trigonal planar. Everybody say it with me. Trigonal, I know you're all muted. I want to see your mouths move. 1, 2, 3. Trigonal planar. Thank you. Okay. Bent, tetrahedral, pyramidal, bent again. Okay, so let's walk through these step by step. All right, so if we have 2 charge clouds, which is what we just looked at an example of, 2 bonded atoms and 0 lone pairs, that is linear. That's how you get something linear. Okay. Here's 2 example molecules, CO2, one we already looked at, and then you also see HCN. So here we have 2 atoms bonded to carbon. We got a hydrogen and a nitrogen. Okay, so that would be 2 plus how many lone pairs on the carbon? 0. So that's how we add up to 2 charge clouds. And we see in a linear molecule, the reason we say it's linear is because the hydrogen and the nitrogen are 180 degrees apart, and that makes a straight line. Okay, now again, I know that there are lone pairs in this molecule. They're right here on the nitrogen, but I am not trying to name the geometry of nitrogen in this case because nitrogen is not central. I'm only naming the geometry of the carbon. Okay. All right, I'm not going to ask you to memorize bond angles either. So the 180 degrees there helps illustrate the point, but that's not something I need you to memorize, okay? All right, so that's the only way you get linear, 2 charge clouds, okay? 3, what if we have 3 charge clouds? There's a couple of ways things add up to 3. If you're looking at the table from above, you could have 3 bonded atoms to your central atom with 0 lone pairs. That gives you 3 charge clouds, and in this case, it's trigonal. The geometry is trigonal planar. An example molecule here is if you have a carbon bonded to 2 hydrogens, and it's also bonded to an oxygen. Okay, The reason we have 3 bonded atoms, let's label them. 1 hydrogen, another hydrogen, and an oxygen. That adds up to 3 bonded atoms. Again, the carbon here, we know carbon never has lone pairs. So 3 bonded atoms plus 0 lone pairs is 3 charged clouds, right? Okay, and again, yes, the oxygen has lone pairs, but we're not counting lone pairs on the oxygen. This is a top view, by the way. You can see why we call it trigonal, okay, the base word there being triangle, because the bond angles are roughly, not exact, but pretty close to 100, roughly 120. And if we drew, whoops, what happened? Sorry. If we drew the geometry over the top of this shape, you would draw a triangle, okay? And these are all in the same plane if you're looking down from the top. Now, a side view looks a little different. Here, the carbon and the oxygen would be in the same plane. And I want to explain something because you're probably going to see this, but I'm not going to have you draw bonds this way. I want to talk about why do we have a dash and why do we have a wedge? Okay, a dash represents atoms that extend backwards behind the plane of the carbon, and a wedge indicates things that extend forward towards you and me from the plane of the carbon, okay? But I'm not going to have you draw dashes or wedges like on that Lewis structure dry lab you did. You just drew in your bonds like normal. Okay, so that's trigonal planar. Let's keep going. Any questions on trigonal planar or linear so far? 2 charged clouds and 1 example of 3 charged clouds. All right. Another way you can have 3 charged clouds was 2 bonded atoms and 1 lone pair on your central atom. An example here is sulfur. And this one is, we call this structure, the geometry is bent. We say that that molecule is bent. Now, I know some of you are looking at this and saying, what the heck? Why does this oxygen have 1 bond and 3 lone pairs? Because everything I taught you last week about Lewis structures with oxygen should always have 2 bonds and 2 lone pairs, right? Well, you learn the more you dig into chemistry that things break the rules all the time. And I'm sorry that this structure shows you an example we have not talked about yet. Sometimes molecules have something called resonance, and electrons can move around. And that's all you're seeing here with this sulfur dioxide is that this molecule has resonance, and this electron could jump here, and these electrons could jump on the oxygen, and you get oxygens that look different ways. Do not worry about that for the scope of this class. I'm never going to put something like this on the exam and ask you about that. So I just wanted to point that out because some of you may notice that. But what you do notice, what you can count, is the bonded atoms and the lone pairs on the sulfur. Okay, we have 2 oxygens, so that is 2 bonded atoms plus 1 lone pair on that sulfur. It's right here. And that adds up to 3 charged clouds. And that is how you get a molecule that's bent, okay? And that is different from the one above because you have a different number of bonded atoms and a different number of lone pairs. Okay, so again, when we view the molecule, we actually don't see the lone pair in the actual geometry, but the lone pair is important for determining what the geometry is. Okay, and lone pairs are pretty bossy and pushy. Okay, they kind of push other atoms around. They need their elbow room. They need their space. And so you'll see that with lone pairs. The more lone pairs you have on your central atom, the closer together the other bonded atoms will be forced to be. Okay, so any questions on this one? We're going to move on to, I think, 4 charged clouds next. Okay, 4 charged clouds. The first example, there's 3 ways things can add up to 4 charged clouds. And the first example, if you remember from the table earlier, is 4 bonded atoms and 0 lone pairs. We call this tetrahedral. Tetrahedral. And the base word of this is, if you actually took a geometry class in high school, you probably know what a tetrahedron is. It's showing you a picture right here. It's a shape that has 4 sides. It looks a lot like a pyramid, but please do not confuse this with a geometry that's pyramidal. That's something different. This one is tetrahedral because it has 4 sides. And if you kind of take that and put it onto our actual molecule like this right here, you see how the, if this is a molecule of like CH4, then you see how the reds are all your hydrogens, and the center black one is your carbon, okay? And then it makes a tetrahedron, okay? And pretty standard, the bond angle between all your extended atoms bonded to the central is a 9.5 degrees. But again, I'm not asking you to memorize those things. So carbon is very, very, very commonly tetrahedral. Not always. Sometimes carbon can be linear, like in that molecule of CO2 we looked at earlier. Sometimes carbon can be trigonal planar. We also looked at an example of that earlier, but very commonly carbon is tetrahedral because you often see it bonded to like 3 or 4 hydrogens or with 4 single bonds, okay? Another way that things can add up to 4 charged clouds is 3 bonded atoms and 1 lone pair. We call this pyramidal. Okay, again, don't get confused that I was using the word pyramid up there with the tetrahedron. Pyramidal is 3 bonded atoms, 1 lone pair. Nitrogen is a great example. Anything in main group 5, often, not always, but often is pyramidal in geometry. Why? Because nitrogen here, let's label them if we need to, has 3 bonded atoms, 3 hydrogens, 1, 2, 3 atoms that are bonded to the nitrogen. So that'll be 3 plus, and here's the 1 lone pair. That adds up to 4 charged clouds. And that is the pyramidal. You can see when we look at the structure overall that we get this pyramid shape. Okay. 107 degree bond angle there. So again, the more constituents you bond to or add to your central atom, the closer atoms are pushed together and the smaller your bond angle becomes when you have more and more things bonded to the central atom. They just have less space to space out or to space out, but I hope that makes sense. Okay, last way to get 4 charged clouds. 2 bonds and 2 lone pairs. Okay, water molecule is a perfect example here. The oxygen is the central atom. Okay, so that's the one we're trying to name the geometry for. And you can see there are 2 atoms bonded to oxygen. What are they? They're both hydrogens, 1, 2. So we got 2 bonded atoms plus 2 lone pairs on the oxygen. So plus 2 lone pairs, that equals 4 charge clouds total. Okay. Now these lone pairs, again, are super bossy, so they are pushing these hydrogens close together, and that's why you see the smallest bond angle that you've seen so far here on a molecule like this. We call this bent. So there's 2 ways you can get bent. You could have 2 bonded atoms and 1 lone pair, 2 bonded atoms and 2 lone pairs. Gives you a molecule with the geometry that's bent. Okay. That's why if you look at this one and you go back and you look at that example SO2 earlier where I was talking about the oxygen, you'll see that the molecules look the same because we don't visualize the lone pairs when we draw the actual geometry, but they do help in determining it. Okay, questions on 4 charged clouds and how things add up to 4. We're going to look at a review slide and then we're going to do some examples after we talk about one more thing. So here's a review slide. All the different ways you can have 4 charged clouds. So I'm not going to spend a lot of time here, but I just want to show you these are all the different things. Tetrahedral, pyramidal, and bent. But one last thing before we actually spend some time working some problems. You can have molecules with multiple central atoms. You see an example here. And when you have that, each atom that is a central atom can have a unique, its own geometry. They're not always going to be the same. So the molecule you see here is a carbon on the left right here. It's got 3 hydrogens attached, bonded to it, and it's also bonded to another carbon on the right. That carbon is double bonded to an oxygen and a single bonded to a hydrogen. If we were going to name the geometry for both of these carbons, you see that they're named over here. How did they get tetrahedral? How did they get trigonal planar? Let's look at this one first. The one on the left, that corresponds to this carbon right here. Tetrahedral. Okay, to be tetrahedral, you have to have what? You have to have 4 bonded atoms, 0 lone pairs. 4 bonded atoms, 0 lone pairs. So let's count the bonded atoms on this carbon. 1 hydrogen, another hydrogen, another hydrogen, and this carbon, they're all bonded, right, to that initial first carbon. So that is how we got 4 bonded atoms plus 0 lone pairs adds up to 4 charge clouds, and that is how they named it tetrahedral. Now, if we're talking about the carbon on the right, they named that one trigonal planar. How did they get trigonal planar? All we do is we count the bonded atoms and the lone pairs. So we got an oxygen, that's 1 bonded atom, a hydrogen, that's 2. And we recount this carbon over here. That one is bonded. From the viewpoint of this carbon on the right, the carbon on the left is the 3rd bonded atom. Okay, so just because you name that one initially does not mean you don't count that as a bonded atom to the second one. So here, for the case of the carbon in green, we've got 3 bonded atoms, no lone pairs. That's 3 charge clouds. That is how they got trigonal planar. When you look at the table, that should give you trigonal planar. Okay, this is a lot. Oh, somebody had a question. What is it?
Yeah, okay. So on that one, you just ignore like the lone pairs on the oxygen? Because I know it's kind of like,
Yes, you ignore these because we're not naming the geometry for oxygen. Oxygen's not central here.
Okay.
You're only counting the lone pairs on the central atom that you are trying to name the geometry for. Does that make sense, Danielle?
Yes.
Okay. Any other questions? It was a great question. Anybody need me to review something? Anybody you're like, I'm so lost, I don't even know what questions I have? Maybe? Okay, well, we're going to work a couple examples, and I hope that will clear some things up. But if you are still just like, I have no clue about any of this, please reach out to me. Let me know. I'm happy to set up a Zoom and re-walk through any of this stuff. So this slide right here, we actually already filled in all the blanks. You should recognize this slide. Earlier, we filled in all the blanks. So this is just the rules step by step. How do you determine geometry? Okay, so we're about to do this. We're about to put these rules into effect. 1, 2, 3. Let's do that for this molecule. We got C3H8O. We're gonna, step number 1, draw the Lewis structure. Once we get the Lewis structure drawn, we're going to identify the central atoms. And we're gonna try to name the geometry for those central atoms. There's going to be more than one. Then we're going to count the charge clouds on each of those central atoms. We're gonna do that by counting the number of bonded atoms and the number of lone pairs, adding that up. Then we're going to look at the table and predict the shape based on our number of charge clouds. So C3H8, you may recognize this. I think this was one from last week in the video lecture we drew the Lewis structure for. At least we did something very similar to it, if not this exact one. So what you should draw is 3 carbons. We know carbons make good central atoms and hydrogens do not. And then anybody have a suggestion? What should I do after this?
Attach the hydrogens.
To the carbons. Okay, Kendall. So we got 8 we got to do. 1, 2, 3, 4, 5, 6, 7, 8. All right, then what?
Then exchange one of the hydrogens for an oxygen, and then attach that hydrogen to an oxygen.
Okay, so we have a problem here. I don't have any spot to put an oxygen. Why can I not do this?
Hydrogen can't have one.
Hydrogen can only have 1 bond, and they all are already bonded to a carbon. You can never put 2 bonds on a hydrogen, okay? So we can't do that. So what we can do, though, is we can remove a hydrogen, plug our oxygen in right there. We know oxygen needs to have how many bonds, how many lone pairs? Yes, 2 bonds and 2 lone pairs. So I can put another bond on this oxygen, and I can put my hydrogen right there. And then I can go in and put my lone pairs. You could have erased any one of these 8 hydrogens and done that. It does not matter where I put that oxygen. Okay, so you could have several different correct structures. for this molecule. Okay, now we did step 1. Okay, boom. All right, number 2, let's find the number of charge clouds. And we're going to count, you can count bonds if you want. I'm going to count bonded atoms.
Did we do that lab before we even had this lecture?
Okay. So how do we count bonded atoms? First off, how many central atoms do I have in this structure?
3.
3. Anybody think something besides 3? Summer says 4. How'd you get 4, Summer? Okay, so I agree with 4. Yeah, oxygen has 2 bonds to it. So oxygen is also going to be considered a central atom here. So we got 4 central atoms. We're going to name the geometry of all 4. 3 carbons and the oxygen are central. So by the way, here's what I know about these carbons. They all look the same. They all have 4 single bonds. So that's going to be interesting. So let's look at the first carbon. I'm going to highlight it in red. This carbon right here. I want to name the geometry of that carbon. So we're going to count the number of bonded atoms. I see 1, 2, 3, and that carbon's also bonded to it. So 4 bonded atoms. How many lone pairs on that carbon? 0. So you should say 4 bonded atoms. I'll abbreviate. That stands for bonded atoms, everyone, not anything else. And no lone pairs. That's 4 charge clouds. So how do we name that? Anybody remember the table? I wish I didn't have it 20 slides back or I would scroll to it. But if you look at the table, yes, thank you in the chat. I see it. We're going to name this tetrahedral. Okay, now let's highlight this carbon in blue. And let's do that one. Same thing. We're going to count the number of bonded atoms, number of lone pairs, name it. I see, count this carbon as 1. That's bonded to my second carbon. 2, that hydrogen, 3. And that third carbon is also bonded to my second carbon. So that's 4 bonded atoms, no lone pairs. Oh, that's the same as my first one. 4 charge clouds. So I'm going to be lazy and I'm going to say, you're also tetrahedral, okay? And carbon number 3. Oh, let's name that one. How many bonded atoms, how many lone pairs? So let's go through and name them or count them. There's 1 bonded atom. That one's bonded to that carbon. This oxygen is bonded to that green carbon. And this second carbon is bonded to my third carbon. So that's 4 bonded atoms. No lone pairs. Oh, that also matches my original carbon. So I'm going to be even lazier and say all 3 of those carbons are tetrahedral. And then we got to name the oxygen. So we'll just highlight the oxygen in yellow. Let's count the bonded atoms. I don't know if you're going to see yellow very well, but no, you can't see it at all. 1, 2. 2 bonded atoms. How many lone pairs? 2. So I'm going to do this in black because I just can't see the yellow. 2 bonded atoms plus 2 lone pairs. That adds up to 4 charge clouds. 2 bonded atoms, 2 lone pairs, 4 charge clouds. How do we name this? If you're looking at the table now. Yep, I see it in the chat. Bent, 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 bent. So bent. And that's it. Questions on that? None of the steps are hard. It's just that there's a lot of steps. So that's where it is complicated, but each individual step is fairly straightforward, fairly easy if you know the order of the steps. And you can use slides like this to remind you and guide you on the exam. Okay. All right, I'm going to skip over number 2. I have a poll question for number 3. So I want you to do number 3 and answer the poll question. So spend some time. Remember step 1, you draw the Lewis structure. Step 2, you start counting charge clouds. I'm going to go grab a water while y'all do that. All right, we've been going for about 45 seconds. Take your time. All right, I'm going to give you about 20 more seconds because then we're going to go over it. All right, go ahead and get your answers in. I'm about to shut it down. We're about a minute and a half in. All right, I know some of you haven't voted, but in the poll. So the share results. The most commonly picked answer here was pyramidal. 60% of you guys said pyramidal. But we had other people pick all the other choices. The second most popular choice was trigonal planar. So let's look at this. The Lewis structure should look like this. You got nitrogen bonded to 3 chlorines. You can see the point I made earlier. If you're still shaky on Lewis structures, this is going to be even harder for you. And yeah, we got lone pairs all over these chlorines, but they are not going to matter for naming our nitrogen. But am I done once I have this? I'm not done. What am I missing on this structure? A lone pair. Kind of says a lone pair. And there should be, yes, a lone pair right here on the nitrogen. So some of you, if you pick trigonal planar, you might have forgotten that nitrogen has 3 bonds and a lone pair. Don't forget that. So now if we're counting this, how many bonded atoms? 1 chlorine, 2, 3 bonded atoms, and we got 1 lone pair right here. So it should be 3 bonded atoms plus 1 lone pair. If we're counting charge clouds, gives us 4 charge clouds. And how do we name that? Pyramidal. If you're looking at the table. Sorry, I'm not scrolling back up to the table. I just feel like that would be a lot to scroll back and forth so much. Questions on that? Okay, there's more examples. We actually already looked at CO2 from the very, very first page when we were looking at the table. I encourage you to take some time and do 5 and 6. You can go back up and do number 2 as well for extra practice. But for time's sake, we still have a couple topics to hit for today. If you are like just losing it on geometry and you just like, I don't even know still, please reach out to me. I'm happy to walk through examples with these. I'm happy to look at more, but just let me know, okay? So we're going to put a pin in geometry. That was a big topic. Lewis structures were a big topic from chapter 4. Geometry is a big topic. Now we're going to talk about the next big topic. And the next big topic is polarity, polar bonds and polar molecules. We're going to start with individual bonds, understanding how they can be polar, okay? The big idea here that I want to point out is that a polar bond occurs when the electrons are shared unevenly or unequally. Unevenly, unequally, doesn't matter. Remember, every bond, like you see with this hydrogen molecule and this chlorine molecule, bonds are formed from electrons, okay? Now, it looks like those electrons are sitting nice and neat in the middle, and they're not. They're moving. but for our sake, we're going to draw them in the middle, okay? So that we can recognize, oh, there's 2 electrons in that bond. Well, when you have 2 identical atoms bonded together, the bonds are going to be shared perfectly evenly, okay, between these 2 hydrogen atoms or between these 2 chlorine atoms, okay? The shared electron pair will be even. If you imagine it as a tug of war match, that's my favorite illustration with this. I want to look at the nucleus of both of these atoms for a second. How many protons are in the nucleus of hydrogen? Anybody remember? Just one proton, okay? In both nucleus, here and here, we've got 1 plus charge, okay? 1 plus charge. That stands for 1 proton. So I want you to think of protons as people on a tug of war team. You've got 1 person pulling both ways. That's a pretty even match, all right? Chlorine, I think chlorine is element 17, correct me if I'm wrong. So you would have 17 plus charges in that nucleus and 17 plus charges in that nucleus, right? If we're thinking of protons as people, you got 17 people on each side pulling those electrons. Because remember, why are we pulling? There's an electrical attraction here. Electrons are negative, protons are positive, so they're attracted to the nuclei of both atoms. So that's why it's like a tug of war match. Now, down here, what's the difference between the 2 molecules up top and the molecule on the left? The main primary difference. Don't tell me that this one's rainbow colored, even though it is. Yes, Bailey got it. It's 2 different elements. Okay? The moment you have 2 different elements, you have the potential or the opportunity, not guaranteed a polar bond, but the possibility to have a polar bond. Okay? Because now the tug of war match is very different. Now we have 1, I'm on eraser. Now we have 1 proton, which is plus charge, in this hydrogen, and we have 17 protons in the nucleus of the chlorine. So which way do you think the electrons are going to be pulled? Yes, I see some pointing. They're going to be pulled towards the chlorine. So here's the deal. Now the electrons are still shared, but they are shared unevenly. They're pulled, they have a gravity to pull towards the chlorine. And they have a gravity, anytime you have something like this, the electrons are going to be pulled towards the element that has a higher affinity or desire for electrons. And it could be based on how many protons are in the nucleus, okay? Does that make sense? That's the basis of what a polar bond is and how you get a polar bond. Now, I want to introduce a word here called electronegativity. So I'm going to scroll down past that periodic table. Electronegativity. You have an entire chart in your textbook right here. What they've done is they've gone through and they've calculated a number on a scale of 1 to 4 to represent electronegativity for all the atoms on the periodic table, okay, except for the noble gases, okay? They don't want to give or trade electrons. They don't want to share electrons, so we don't even give them electronegativity. What do you notice? Which element has the highest electronegativity on the whole chart here? Yeah, fluorine, okay? Fluorine has a 4. So fluorine wants electrons. It's the element that wants them the most. So any element that's close to fluorine is going to have a high electronegativity. And as you move away from fluorine on the periodic table towards the elements in group 1, you're gonna be less attracted to electrons. Does that make sense? You have a lower and lower electronegativity. So I'm going to erase this because I want to look at some other things here. But you're going to have this chart on your resources page for exam 2. Okay, this is going to be an important chart. Because like I said, the moment you have 2 different elements in a bond, you have the potential for it to be polar, but how do I actually know if it's polar or not? It all has to do with calculating what we call an electronegativity difference. Electronegativity difference is how we measure how polar a bond is. And then we'll classify it according to a table that I'll show you in a second. So how do you calculate electronegativity difference? Well, you just go get the values from the table and you subtract. Okay, you do the lowest number subtracted from the highest number. The lowest element subtracted from the highest element. So here's 2 examples. We got carbon bonded to nitrogen and we have carbon bonded to oxygen. We're going to calculate, this figure shows you the electronegativity difference for each atom and essentially for each bond. So for carbon, if we go up to this table Carbon's right here. It's got a value of 2.5. And then we see it's bonded to nitrogen, so it's got a value of 3.0. And then we're also going to need oxygen in a second for the figure on the right. It's got a value of 3.5. So come back down here, and you can see nitrogen was the 3.0, carbon was the 2.5. So we subtract them, highest minus the lowest, and you get a difference of 0.5. And if we look at the figure then on the right, carbon and oxygen, we do the 3.5 is the oxygen, and the 2.5 again was the carbon. You subtract those, you get a difference of 1. The larger the electronegativity difference is, and in fact, that's the blank down here, the larger or the bigger the electronegativity difference, the more polar a bond is. So that's why when you look at this overall, we're going to say the carbon-nitrogen bond had a smaller electronegativity difference, so it's less polar. The carbon-oxygen bond has a larger electronegativity difference. 1 is bigger than 0.5, so it's more polar. Now, some of you may be wondering, what are these little symbols and signs right here? Anybody actually know what these are? Some are like, that's a Greek letter, I know that. Yes, partial charges, okay? What is a partial charge? So these little squiggles it's a lowercase Greek letter for delta, okay? So you can say delta positive, delta negative. Some people say that. I tend to say what you see in the chat. I say partial positive and partial negative. So that's the phrasing that I'll use for these. But if you read different places on the internet, you might read slightly different things. Semi-positive, semi-negative. Some people say that. So the partial positive and partial negative signs, we can label those things on any particular bond when we have a polar bond, okay? And the element that has the lower electronegativity, I'm gonna say that again, the element with the lower electronegativity, so the 2.5, oh, I'm on highlighter. The 2.5 in this case, the carbon, we're gonna give it the partial positive sign, okay? And that is the squiggle with the plus. And the element with the higher electronegativity is gonna get the partial negative. Okay, makes sense? And you see the same thing over here with the carbon and the oxygen. All right, so now you can calculate an electronegativity difference, but how do you know if it's polar or not? That's where this table comes in, okay? Based on the electronegativity difference, this is straight from your textbook. If the difference falls between the range of 0 to 0.4, we call that a non-polar bond. Your book will say covalent. You're going to hear me say non-polar. Non-polar covalent is kind of the complete term. What this means is that the electrons in the bond are shared pretty evenly. Okay? You may have 2 different atoms in your bond, but the electrons are still shared pretty evenly. All right, if the electronegativity difference falls between 0.5 to 1.9, 0.5 to 1.9, that is going to be a polar bond. Okay, this is where the electrons are shared unevenly. And now, I didn't spell that right. And now we have a polar bond. Okay, so both of the bonds up here, we had a difference of 0.5 and 1. So those are both polar bonds. And if the difference is 2 or above, we say that's so, I just threw my pencil. We say that's so polar that it is now ionic. Now you have ions. Now the electron has completely jumped ship. And it's gone from one atom to another. And you have a cation and an anion. Okay? But an ionic bond is essentially a polar bond on steroids. It's so polar that it's now ionic. So if I had you list bonds in order of increasing polarity, you would list nonpolar bonds as the lowest polarity or no polarity. Then you would list bonds that are polar. Then you would list bonds that are ionic because they're beyond polar bonds. Okay. All right, so if you're looking at these 3 bonds down here beneath the table, it just shows you it's already calculated the electronegativity difference for you. And if you had to classify them as nonpolar, polar, or ionic, I think you could do that, right? You're just looking at these numbers and seeing where do they fall in these ranges. So obviously carbon to fluorine would be polar. And these other two bonds are above 2, so these would be ionic. Okay, any questions on polar bonds? We're going to do a practice problem. So I've got the electronegativity chart. I'm going to launch a poll. I want you to tell me which of these following bonds is polar. So you need to calculate the electronegativity difference for all these bonds and then see which one falls in the range of 0.5 to 1.9. We're about a minute in. I'll give you about 20 more seconds and then I'm just going to shut it. All right, I'm about to call it. Go ahead and put your answer in, even if you have to guess at this point. All right, in the poll, share the results. Okay, the most commonly picked answer, 75%, said the nitrogen-hydrogen bond. But some people picked all the other choices. So obviously, number 1 should not have been picked because it's 2 carbon atoms. And the difference there is 0. That's 2.5 minus 2.5. So that's a difference of 0. So that's definitely not polar. So anytime you see atoms that have, or bonds that are between identical atoms, carbon to carbon, hydrogen to hydrogen, you can automatically know. You don't even have to calculate it. That's a non-polar bond. Okay. Now nitrogen and hydrogen, we're looking right here, 3.0 and 2.1. So you should have done 3.0 minus 2.1, and that's how a lot of you got 0.9, and then you looked at the table and you said, oh yeah, that's definitely polar. And then you got your answer and you didn't have to do anything else at that point. Okay, this was the nitrogen, this was the hydrogen. So that one's polar, but I do want to make the point. The next bond on the options are the carbon-hydrogen bond. Carbon has a value of 2.5 from the table, hydrogen is 2.1. So when you subtract those, you get 0.4. That's almost polar, but it's not. It's non-polar. How many times have we dealt with carbon-hydrogen bonds already in chapter 4? A ton. Okay, when you draw Lewis structure, you normally have so many carbon-hydrogen bonds. Often, not always, but a lot. And I just want you to know, this is never polar. Carbon-hydrogen bonds are never polar. And if you just get that down, if you memorize it right now, that's going to help you in so many ways. It's going to save you time. You won't have to calculate it every time. Just know it's never polar, okay? And then sodium chloride is so polar, it's ionic. All right, so I'm going to stop sharing that, and let's look at one last thing. We only have about 10 minutes left, so hang with me. Take a deep breath. We're almost there. We need to now address polar molecules, and that's all we're going to have time for today. We still have one more topic in chapter 4 after that, and I'm just going to have to make a video, again, 10 minutes long or so, and I'll throw that on Blackboard by this evening. Please watch that before Thursday about how to name covalently bonded molecules, and then we're going to move on to chapter 5 on Thursday. So last thing, here we go, last 10 minutes, polar molecules. So now we've talked about polar bonds, but we can get even more big picture than that. Now we're going to see how do we know if an entire molecule is polar or not. There's 3 ways to determine this. Number 1, you need to ask yourself, do I have any polar bonds in my molecule? So you're going to look at what kind of bonds do you have. And when I say what kind of bonds, I'm not talking about single, double, or triple bonds here. I'm talking about what atoms are involved in your bond. Like, do I have a carbon-hydrogen bond or a hydrogen-hydrogen bond? Okay, that's what I mean when I say what kind of bond. Number 2, do I have any lone pairs? Okay, a lone pair is where electrons are. So if you have lone pairs in your molecule, that is a region of high electron density. That is a region you're going to be able to put a partial negative sign on, and it's likely that your molecule will be polar. But not always, because you have to consider the third thing, which is the shape of your molecule. There will be times when you'll be able to look at a molecule and say, yes, I have polar bonds, and yes, I have lone pairs, but because of the shape of my molecule, I have no net polarity overall, and I have a non-polar molecule. And that's if or when you have symmetry in your molecule. So I'll explain what I mean on that in a second. Let's look at some examples. Okay, just remember, if you're assessing this, I will ask you these kinds of questions on the exam. You need to go step by step, look at number one, do I have polar bonds? Do I have lone pairs? And look at the shape. So let's look at water. Water is H2O. I'm looking at this molecule of water, and I see that I have what kind of bond in my molecule? And remember, I'm not talking about single, double, triple. I see that I have an oxygen-hydrogen bond. And I've got two of them, okay? Number one right here and number two right here. Two oxygen-hydrogen bonds. So I'm trying to decide, is this a polar bond? Is an oxygen-hydrogen bond polar or not? Okay, so how do we do that? We go look at the electronegativity values. Okay, so I'm not going to take the time to scroll up to the chart and all that right now. I'm just going to tell you from practice, oxygen, I believe, is 3.5. Hydrogen is 2.1. You do the difference, you get 1.4. That's definitely polar. So yes, both of these bonds, we're just going to label, both of these are polar. Right? Okay, now do I have any lone pairs in my structure? And obviously, yeah, I see two lone pairs. So because I have polar bonds, I know that the electrons in these bonds right here, they are going to be pulled towards oxygen, because oxygen is the more electronegative element. All right, so these electrons are not shared evenly. They're pulled towards oxygen. On top of that, I got lone pairs on my oxygen. So this is definitely appropriate to put the partial negative signs up here. And if that end of the molecule is partial negative, then the opposite end is the partial positive, these hydrogens, okay? You got to write the partial positive signs on the hydrogens. Now, when we can do that, when we can separate the partial positive and negative across our molecule like this, we can draw in something we call a dipole. This arrow right here is called a dipole. And all the dipole is doing is it's indicating to us which end of the molecule, which region of the molecule, if we separated our molecule into two chunks, a top chunk and a bottom chunk, and we drew the dipole, we would point it towards the region that is the partial negative. So the arrow points towards the region that's partial negative, and then we put this little plus sign, we cross the arrow, making a little plus sign, and that's going to be on the region that's partial positive, okay? So you point it towards the partial negative region, you got the partial positive indicated as well. All right, and if you can draw a dipole that is permanent and does not cancel out, then overall, yes, this molecule is polar. Water is a polar molecule, okay? Next example, chloromethane, CH3Cl. Again, what kind of bonds do I have in my molecule? Okay, if you draw the Lewis structure, we see the structure here. I've got two kinds of bonds. I've got carbon hydrogen bonds, and I have a carbon chlorine bond right here. You'll see that bond? Remember, we said these are never polar, but a carbon chlorine bond is polar if you go do the little, if you calculate the difference. So this bond right here is polar. And here's what else I know about chlorine, but it's not drawn in. We're loaded with lone pairs on that chlorine. So yeah, I got a polar bond and I have lone pairs. Do I have any symmetry in my molecule? The shape of it is not symmetrical. I'll show you an example of a symmetrical molecule in a second. Because of that, I can draw all these partial positives on the hydrogen. These are very, you're going to hear me say this phrase, electron deficient or electron poor. Okay? All the electrons are moved towards or shifted towards the chlorine. That chlorine is very electronegative. It wants to hog the electrons in the structure. So this side up here with the chlorine is electron rich or electron dense. And therefore you can draw the dipole in like that. It doesn't cancel out with anything. It's not symmetrical. And so yes, this molecule is polar overall. Okay? That's how you go about deciding is a molecule polar. And that's a lot of steps. It builds on everything we've talked about so far. In the last 3 or 4 minutes I have, let's look at what happens when you do have symmetry, when shape does come into account. So let's look at CO2. CO2, I'm going to draw my lone pairs in on my oxygens. I know these should have lone pairs. That's going to help you. Okay, what kind of bond do I have in my molecule? I have a bond. Again, I'm not talking about double bonds. I have a carbon-oxygen bond. That's the only kind of bond I have. Okay, now you need to ask yourself, is that a polar bond or not? Well, let's calculate the electronegativity difference. We actually did this earlier, the example. We've got 2.5 and 3.5 are the values. So you do 3.5 minus 2.5 and the difference is 1. So this is polar. These bonds are polar. Now, if we're looking at these bonds and we know there's electrons loaded in these bonds, right? Where are they going to be pulled? Are they going to be pulled towards the oxygen or towards the carbon?
The oxygen.
They're going to be pulled towards the oxygens in both cases. They're going to be pulled this way, and they'll be pulled this way. Okay, all the electrons. So because of that, we can assign these partial positive and partial negatives on these different atoms. We got lone pairs on the oxygen. The oxygen is really electronegative, so it's pulling the electrons in the bond towards itself too. So we got a really uneven distribution of electrons here. Okay, so now can we draw a dipole in overall? I want you to draw dipoles in. How would you do that on this molecule? Remember, we always point them towards the partial negative region. But would I draw it this way? Or would I draw it this way? Well, the answer is you'd actually do both. You could draw a dipole in like this and like this. So what do we do when that's the case? Well, now I'm going to take into account the fact that I have symmetry in my molecule. If I draw a line of symmetry right here down the middle, you see that both sides of the molecule are identical. And when this happens, when you have two arrows pointing, two dipoles pointing opposite directions, we say these cancel each other out. The dipoles cancel. And because of that, we have 0 net polarity. Okay, so this is non-polar molecule overall. Same idea with CCl4. If you draw the Lewis structure like this, I like to do that better. Last thing, and then I'm done. You can see if you draw all the dipoles in, these are polar bonds, carbon, chlorine. We actually looked at an example, calculated it right there. We said that's polar. So if you draw in all your dipoles in, one right, one left, one up, and one down, this looks really crazy, I know. But here's what you see. There's 2 planes of symmetry. The top and the bottom cancel. Those dipoles, and then the left and the right, those cancel. So there's no net polarity overall, non-polar molecule. Okay, so that's kind of what this slide's saying. If symmetry exists, overall, no net polarity within the molecule. All right, I had more, and you can look at these.